Okay, good afternoon. So, let's continue where we stopped last week. Smoothing. Smoothing is a bit a topic which is, as you've seen, not too difficult mathematics, but it's quite essential because data is noisy and we want to get a clear view of it, and hence getting rid of the noise of the data is an important step whenever you work with real world data. So this is why I put a bit of point into this smoothing. And let's start here. Let's look a bit into what we have here. You remember what we did last time? We got ourselves some random example function like this one, which had a bit of steep parts and flat parts and everything. And then we imagined that we measure this curve, but we get only randomly noisy data. And the noise works very well that we sort of measure at a certain point x and we get a value y, which deviates from the curve by some random noise, which we simulated by adding a normally distributed noise. And then we looked at different ways how to do that. First, we said, let's just bin the x-axis in different bins and take the average of each of them. Then we said we do the kernel smoothing, where we put over each point of x a kernel, which gives us weights and which allows us to get a weighted mean, which takes which counts all the existing data points according how far they are from the point from the curve point we want to get. And then we got this here. And then we went to local regression, where we said instead of simply taking a weighted average, we make a weighted regression where we fit a line or a parabola or some other polynomial to these points with their weights. And once we do that, we just take only one point of this whole fitted line, namely the point at the midpoint of our kernel, and store this as the point of our smooth curve. And that way we then get a red smooth curve. A nice thing is, on the first hand, it looks a bit like as we calculate for each x point a separate y point by doing a new regression, the values for different x points are not at all connected. So it's a bit nice that nevertheless you get a smooth, or at least a continuous and a differentiable curve out of it. But it's easy to see that this should come out if your kernel is smooth and smoothly goes back to zero at the end. Then of course any new data point while you move the kernel will smoothly get in there and increase its weight. And so the curve that you get out of this procedure will be smooth as well. So we also talked about adaptive bandwidth, where we said instead of making the kernel with a fixed width, we simply always adjust the width so that always the same number of data points are under the kernel, so within the support interval of the kernel. And in the last thing, I think we stopped here mentioning that in R there's this logfit package, or the lowest function, which do all this thing in one go. The lowest function has always been a part of R. Logfit is a separate package, but has been around also since 20 years or so. And it does exactly what we've described so far. And yes, and we tried a bit with bootstrapping and uncertainty estimation to see how well this works. And the point where we stopped last time was saying, in our simulation, we simulated our noise to be normally distributed. That's a good way anyway, by the way, to whenever you work with a new procedure in applied mathematics, it's always a good idea to start by simulating data and then seeing whether your procedure recovers what you try to simulate. And the reason why this is useful is for two reasons. One is it's a good way to check whether the procedure really does what it should do, but it also forces you to think about a model. And that's something that applied mathematics people often don't do. Whenever you work with real data, you need a model which tells you how you think this data was generated. In our case, our model was for every input value x, there is an expected value y, and what we measure is this value y plus some random noise added, and we assume the random noise to be normally distributed and to be homoscedastic in the sense of that the standard deviation of a noise is independent of a y value. And these points, these assumptions are always important to realize about them, because it allows you to think about how to adapt your procedure when the assumptions are not met. And this is what we have here, because in our single cell data, we always work with data, with count data, and we assume that this count data follows a Poisson distribution. And the Poisson distribution is not homoscedastic. Rather, the variance is proportional to the mean. So higher mean means higher variance. So in that case, if this was Poisson distributed data, then up here at the top of the curve, we would get more noise and it would scatter more than here at the bottom of the curve. And of course, we want to have a procedure which takes this into account. And to see how we can do the procedure, I do what I did before. Instead of first explaining the procedure, I start by simulating such data. So what I will do is first, as you see, I've decided to take a few more data points, now 300 instead of 100. And again, I draw x-axis, which I take from the uniform distribution between 0 and 1. And now what we will keep in mind is this idea of pseudo-time that we talked about 2 weeks ago, or no, it was also last week, where we said sometimes single cells follow some trajectory, some continuous trajectory where we move through feature space, and we can look at the cells and assume that each of the cells that we observe is at a different point in this progression. And x is our pseudo-time. It tells us how far the cell is in its progression, from 0 meaning the beginning of a journey and 1 meaning the end of a journey. And in that way, we get our, and so this x-axis is now meant to be this time here, going from 0 to 1. And because you remember with these cells, we always had this total sequencing depth, so the total number of reads we get for a cell, which were the column sums in this count matrix. And to simulate realistic data, I also should draw them from something, and I've decided to draw them from a log normal distribution, with the mean here at 1,000, and you see it goes between 500 and maybe 3,000. And we need now a true function which tells us what the expected count value is for a given pseudo-time. And I take the same function as we used before, but I exponentiate it. And I exponentiate it so that we get a bit more difference between the value range, so that we have more dynamic range, which makes the problem more challenging. Then after exponentiation with the x, it looks like this, and you see I have shifted it a little bit along that value range, so that all the values are sort of in this area of what we are used to from single cell, that the gene might take up maybe 1% or maybe 10 to the -5 of all the counts that we get in total from the cell. And now with this, we can now use our Poisson noise. And even for I said we add the Poisson noise, I don't really add it this time. What I do instead is I make a hierarchical mixture. So first I drew arbitrary x values and now got the expected corresponding y value, which I call q here, for each of the cells. And if I multiply this q by the size of the cell, and of course, as q is the proportion, q times s is the expected count of the cell, and I go with through the Poisson function. So the Poisson function will now take this matrix q times s, which is a vector of length n, and it will draw for each value q times s one count value out of k. And in order to visualize what I've now got my data, I undo what we've always done. I take the k, divide it again by the simulated read totals s, and make our usual thing of adding a small pseudo count into a -4 in order to have a decent, what I want to say, in order to avoid the zeros. And what I then get is this here. And as you can see, this follows here the value, and we have again our problem with the zero. All the cases where we got zero counts, they now sit here at top, at the bottom. And this gap here between 0 and 2, between the cases of 0 count and of 1 count, this gap is more or less driven by this scaling factor 10 to the 4, which is arbitrary. So this gap is also arbitrary. And now you can see where our problem begins. If I now were to use the normal fitting procedure that we've discussed last time, then this thing would simply go through here like this, through the middle of it, probably somewhere in the middle of this gap, which wouldn't be appropriate, especially it would depend on this arbitrary counter scaling factor. And so we need something better. And the better thing that we will use for this is we will use two different ways. I first show you a simple thing and then it's slightly more involved. Yeah. Yes, it could happen that maybe we have way more X values here than here. This especially happens when a cell moves slowly through the state space for a while and then suddenly moves fast. You remember last time, this is why I introduced this last time, the idea with the adaptive bandwidth, where we always make the kernel wider or smaller depending on this. We will need this for real data. But for the simulated data, I excluded this complication for the moment. So the first thing that we can do is, again, we do a simple kernel smoothing without regression, where we simply take a weighted average over the values of yi, and we weight them with wi, where wi are the kernel weights around, putting a kernel around the query point x0 with a certain width. So, and then wi is the value of the kernel function at the position x0 minus xi divided by the bandwidth. But we now make a slight change. Instead of using this function, we use this function here, because normally you would say y is k over s. So I put k over s here on top and multiply this with this weight and divide this. And instead I will use this part here, which puts the s at the bottom instead of at the top, which sounds a bit weird, because it feels strange that we can simply pull it out of a sum and push it under the other sum. And there's a reason behind that. But I first try it out here, so you see how it works. I have my kernel smoothing function, which takes a query position x0 on the x-axis, and then the vector x of pseudo-time values, the vector k of observed counts for the gene, S is the total, and S a vector of cell totals, and H is the scalar, which is the kernel bandwidth. We calculate the kernel depending on the distance of the data points from the query position, and then I now calculate this function here, the sum of the weighted k's divided by the sum of the weighted S. And if I do this, what I have to do is I take again a grid of x values, just 300 values linearly interpolating from 0 to 1, and I plot this here, calling for each of these 300 values my kernel smooth function, and then I get this red function. And you see that works reasonably well, except here at the bottom it moves quite a lot, and this is to be expected because here the noise is much higher than up here. So, but why did I decide to move this S at the bottom? And for this, we take a small detour called inverse variance weighting. What do you want to do? Yeah?
So, you mentioned the
yeah.
The noise is lower or higher, but I'm a bit confused. I thought also the buzzer noise, the variance will be greater the higher you go.
Right, I should have mentioned this. It might seem like this, but notice that we have a logarithmic axis. What this now means is the noise is, the variance is proportional to the mean, so the noise, the standard deviation, is proportional to square root of the mean. So the relative noise goes down with the square root of the mean. And once you take the logarithm, relative noise turns into absolute noise. So what we see here as noise is basically by which factor we have to multiply the true value to get the noisy value. And that is why we see now here, if we look at the actually moved case, that the points up here are smaller together, while here they spread over, at the bottom they spread over a larger region. And that's quite crucial to always keep in mind when you're talking about the Poisson. On absolute scale, the noise increases, but increases with only the square root of the mean. So once you take the logarithm, the noise decreases, which is also one of the reasons why I used the logarithm here, because usually you're interested in relative noise and not in absolute noise. So in noise considered as a proportion of the mean. So where was I? Exactly. Now what we've done here is we have a number of random variables with yi here, and we want to get a weighted average of them. And we wonder what might be good weights. And to do this, and as a precaution, we first imagine the following problem. We have a couple of independent random variables, xi, and we know that these variables, I may quickly reload this because there's still a typo which I had just fixed last time. Don't tell me I don't have internet here now. Only web. I hate this thing. Either room in this building is a bit a problem. That's why we now have to. So, new try. Okay, yes. Now it's correct. So we have a couple of random variables xi, and we know that they don't have all the same variance, but each of them has a different variance vi. And we want to estimate the expectation of the mean. So you see, this is the mean of all these n variables and their expectation. And for this, we want to weight them. And it seems to make sense that in order to estimate the mean, we should put a higher weight on the precise variables and a lower weight on the variables with high variance. So our weight should somehow be in a reciprocal relationship with the variance. And if we do this, we can look at the weights and can wonder what weight should we put in order to get this mean as precise as possible. So what will minimize the variance of this estimator? Which W's will minimize it? And it turns out, and I will show you the proof in a moment, that so of course, if all the variants are the same, then you simply use constant weights and use a normal minimum. But it will turn out if the variants are different, then we should put the weights exactly to 1 over the variances. Yeah?
The xi have the same mean, otherwise I don't see how it would be justified in weight.
Good point. Yes, of course, they need to have the same mean. I should add this here. If they aren't, you could still technically still calculate here this thing, but it wouldn't be well motivated to do the thing. Yep, so we have sort of the same mean. The sort of will come because in the moment what we will later do, we will use this for our kernel smoothing. Of course, in the kernel smoothing, we also know that they don't really have the same mean, but we assume that towards the center of the kernel, the mean is at least roughly similar. So why do I have put the weights proportional to 1 over v? I was too lazy to write the proof. Wikipedia comes to our rescue. I also forgot to point out that the variances that our random variables are all uncorrelated. And here you now see if we consider a weighted sum like this, and we assume now so that I can omit the denominator that I had in my case. You see, I have a denominator here. Wikipedia solves the problem by just stipulating that the denominator has to be 1. And then we can see that the variance of the sum is simply given by the sum of the variances of the individual values, each of them weighted by the square of the weight. And we now wish to minimize this thing. And what we have to do for this is, of course, to say the gradient of the variance using Lagrange multiplier principle, we have this constraint that the sum of all the weights is 1. And you remember, if you do a constraint minimization, the logic is we don't find the 0 point of a gradient, but we find a position in the gradient where the gradient is collinear with the constraint. So the derivative of our constraint is, of course, just given by 1. And the derivative of this thing here is given by this. So here we have the derivative of our objective function. This here is the derivative of the constraint. And with that, we now see that the weights have to be proportional to 1 over the variance. And here with W naught, I didn't quite like it. They call it W because it's not a weight. This one is the Lagrange multiplier. So read it as a lambda if that's more what you're used to for Lagrange multipliers. Okay. So this is why we use this. And now if we go back with this logic to our Poisson variables, and we said we want to make this weighted sum here of these values k over s, and we want to find the proper weights. And to do them, we say these weights should be proportional to the variance of k over s, which of course the variance of k over s squared. K follows s times q. So this cancels, and we get here that the weight should be proportional to the size factors. Because if you have many cells which all express this gene at the same fraction, then the cell with a deeper sequencing will have a more precise estimation. So we insert these W's here in there, and now insert for W here S, and the S cancels and appears here, and now you get this thing here. And this is the reason why whenever you take the mean over, whenever you have multiple estimations of a fraction, and you want to take the mean of them, then you should use this formula by adding up. So go back to our usual example. We have a bag with millions of balls, of which an unknown fraction is red. And several people all go in and draw a certain number of balls. Each person draws a different number of balls and reports how many balls they've drawn and how many of them are red. And you want to combine all their data in order to get the optimal estimate for the fraction of red balls in the big bag. And then it comes, you have to calculate the sum of all the red balls that all of them have drawn together, divided by the sum of balls they have all drawn together. And this now justifies that if we want to estimate Q hat, we use this here. But now we have two variances with two kinds of weights. The weights which should account for the fact that the variance differ from cell to cell, and the weights which should account for the fact that the cells differ in pseudotime and only some cells are close to the pseudotime we want. So we keep this as it is and put in the weights, the other weights, the weights derived from the kernel rather than the variance. And with that, we now come to this formula here. Where I put the weights from the kernel now on both sides and the S are at the bottom. Questions about Weber? Yeah. Yeah. Theoretically, I try to always say I use capital letters for random variables, and I use small letters for either constants or for realized random variates. So K is the random variable, and capital K is the random variable, and small k is the actual observed random data value. But I think I haven't been quite consistent with this. And of course, as usual, the hat on a variable indicates that it's an estimator. That is an estimate, so a value obtained from the sample values, which is meant to get close to a population parameter. Now, so this was the equivalent to our original idea with the kernels moving. But back then, last time, after we looked simply taking the kernel-weighted average, we decided next to do the kernel-weighted regression. And we said that a regression might work better. Now, and we did this with an ordinary least square linear model. And the ordinary least square model, of course, depends on the idea that our noise is normally distributed, but now it's Poisson distributed. So how can we modify ordinary least square such that instead of we can account for the fact that our noise distribution is not normal but Poisson. And this is done by a generalization of linear models, which is, as always creatively called, generalized linear models, usually abbreviated GLMs. And to demonstrate this, I want to first explain GLMs in general without going into pseudotime, because with the pseudotime in our curve, we used a local regression with kernel weights. But now let's first talk about an ordinary total regression. And we use an example that I'm sure you all have done at some point in high school or whenever. We have radioactive decay. We have some radioactive sample, and we measure the activity of these radioactive samples. And you remember, activity measurement works as follows. You have your sample, your thing of radioactive matter, a little rock, and every time an atom decays, it emits some radioactive radiation. And if you have a Geiger counter, the Geiger counter makes a click. And if you put the Geiger counter next to the thing for a minute or so, and you count how many clicks you get a measurement for the activity. Of course, it's not the total activity, because you only get those radiation which flows in the direction of the Geiger counter, not in the other direction, but it's good enough for us now. So the number of clicks that we get in a fixed time unit is proportional to the activity. And the activity, again, is proportional to the total number of radioactive atoms which are still in the sample. So while the sample decays, exponentially going down, also the activity goes exponentially down. So if I imagine that the amount of radioactive material goes down here with this time constant 1/20, so it's half-life 20 time units, might be minutes here or whatever, or hours. Let's say these are hours, and the half-life of our material is 20 hours, when of course the amount of radioactive material follows 2 over minus T20 over 20, and the expected number of clicks per minute also follows something like this here. So no T is hours, this here is minutes, so it's not that our Geiger counter sits there all the time, but we put the Geiger counter at a certain time point, wait for a minute, when we go home, an hour later we come again, put the Geiger counter, count for a minute, when we go home again, and so on. And we can see how, and so we can use the exponential to calculate the expected number of counts, but the actual number of counts is now a Poisson variable. This is a classic example for something where the Poisson distribution is not merely an approximation for the binomial, but we can theoretically argue that this is exactly distributed like a Poisson. Actually, not perfectly exactly, but it's exactly if we assume that within this minute, the overall activity doesn't change much. That's why I said T is in half-life is in hours, and we always only count for a minute. And so because of this, the number of counts we get doesn't exactly look at the exponential, but it scatters a lot, especially here at the bottom. Sometimes we get few counts, and then we get more counts again. And this is what we get out of this Poisson. And so this is a nice example of how the Poisson works. And if I now want to have this data, and this is what I've measured, and I want to estimate the half-life, how do you do this? I think the standard example that you usually learn if you do physics and in the first semester practical, you're supposed to do this, or maybe already even in high school, people tell you make a semi-logarithmic plot, so make the y-axis logarithmic, the x-axis non-logarithmic, and put the numbers and then draw a line through it, and the slope of the line tells you the half-life. The catch with this method is, what I do with all these cases up here, where we where the number of clicks was 0. Here, we can't use them, so we exclude them from our curve fit, but that's not a good idea because A, it's information that we throw away, and B, it gives us an upwards bias because we only count those things which have a count which are clicked, and they are of course above the expectation because there's others which are below. So simply making a line works if you have many clicks, but here on the right half of a plot, it doesn't work anymore. What we do instead is we fit a proper model. We say our model is that the clicks that we get at time point ti follow a Poisson distribution with alpha times e to the kappa times ti, where kappa is the time constant, and alpha is the initial, the amount of clicks or the rate of clicks at time 0. And for our simulation, of course, alpha is 100 and kappa is ln 2 over 20. Remember that in the simulation code above, I said 2 to the to t over 20, and now here it's e to the t, so I have to divide, I have to multiply with ln 2 to get this. Now, and what we can now do is that we use maximum likelihood. Maximum likelihood means that we write down the probability mass function for the Poisson. So you know what the probability mass, let's write it on the blackboard again so that we have it for as reference here. The probability mass function of the Poisson is e to the minus lambda to the k over k factorial. So we use this probability mass function and insert the values for k, for the values ki that we have here, and we multiply all, and for lambda we insert our expected click rate, alpha times e to the kappa over ti, and this gives us the probability of observing ki at time ti, and we multiply all these things in order to get the overall probability to see these. So the probability of observing k1, kn is kappa ti. So, and this probability here, because the case, you can first read this as a function in the k, and then we call it a probability, because it's a function in the k, and alpha and kappa are parameters which are fixed. But now we do it the other way around. We are given, because these data, they are fixed, this is our observation, and alpha and kappa is unknown, we want to find it out. So we read this expectation, this expression here as a function of alpha and kappa. Yeah.
Second line on the right-hand side of the equality, these Poisson distributions should be evaluated.
It should be evaluated at the time ti, which is the time when the click rate ki was counted. And, I know what you mean. Ki, this is how I should write it. So this is where I put it in, and to make it consistent, I write this here as k lambda. So, and I would consider this either as a function of case, when I call it a probability, or I consider it as a function of the parameters alpha and kappa, when I call it a likelihood. And now, if you actually calculate such a likelihood for a given value of alpha and kappa, you get a very small number because all these probabilities are smaller than 1. So what you do in practice is you don't use the likelihood, you use the logarithm of the likelihood. And then you get log L alpha kappa is this product turns into a sum. And this here is then the minus lambda minus lambda e plus k times log lambda e minus ki factorial, with lambda I is alpha times e to the minus kappa times ti. So, this is what we call the log likelihood, and we consider this a function of alpha and kappa, and we maximize it. And that's what I do here now. Here is the log likelihood. It takes alpha and kappa, and this here d plus means the Poisson mass function at position k using this rate parameter. And don't give me the function itself, but its logarithm. So this here, this is just R syntax for this here. Yeah.
Sometimes the power we take d2 is minus kappa ti, and sometimes it's plus kappa ti.
There's a minus missing here because I put the kappa here positively. But actually, it would be better for what comes if I put the minus here. Let's imagine the minus is here, the missing minus. So kappa is negative. So, and now we can optimize this function. And the easiest way to optimize this function is trial and error. We just tell the computer, try random value pairs for alpha, random pairs for alpha and kappa, and try around, always trying to increase the value. So the function, the computer sits at some two value alpha kappa, tries to increase or decrease alpha, increase or decrease kappa, checks whether the value goes up or down. If it goes up, it continues in this direction. If it notices it goes down again, it knows that it is overshot, so it goes back, makes a smaller part, etc. You can imagine you can use this as, there's different optimization methods. The most common one, which you might all know, is gradient ascent, where you always calculate the gradient of your function and then go a step in the direction of a gradient. And you can use the Newton's method to also figure out what might be a good, step size. But here I can't use gradient ascent because it would require me to calculate the derivative of this likelihood with respect to alpha and kappa. Calculating this derivative is of course no problem at all, but I'm too lazy. And so what I do here, I use R's optim function, and the optim function works as follows. You give it a starting point, just random starting points, and then you give it a function which takes x. Now, because x will now be a vector of two values, we have to write here, we want the first vector of x to be used for alpha and the second vector to be used for kappa. And then we want this here to be maximized. And this optim function can use different methods for optimization. If we give it only a function, it uses a method called Nelder-Mead. If we give it a function together with its gradient, so if I weren't so lazy, I would here write a second function which calculates the gradient. And then it would use one of these gradient-based methods like Newton's method or the refinements of it like conjugate gradients or BFGS, or there's a lot of gradient following methods. But because I was too lazy for it, it has to use the Nelder-Mead method, which is a method which can work without gradient. What that one actually does, it starts off with a triangle, so it's a two-dimensional area. It makes a 2D simplex, so a triangle. And it has some clever way of inferring, if it sees this triangle, whether the maximum might be inside or outside, because if you have a triangle and one of the values is one of the corners has a much lower y values than the other, then it takes this corner and flips it by mirroring it the line between the other two and mirrors it down there. Does something like this. It starts like this. It calculates the function for all three corners. So this would be alpha, this would be kappa. When let's say this is the smallest value, when it flips it over here and says, let's try next these ones. And if now this is the smallest, then it says, let's try next these ones. And if it notices, oh, this didn't work, I tried it, and now this one is actually now even smaller, then this means that it went up here and down here, so probably the true value, the maximum is somewhere in here, when it shrinks the triangle, by shrinking this to half of it, and checks maybe it's in here, and in that way it always makes steps of either flipping the triangle or shrinking it, until it's, the 3 points converge to 1 point in the middle, and then it reports that. This is a very nice, neat little function, because if you just want a quick and dirty result and don't want to bother writing out the gradient, then this Nelder-Mead is a good way of quickly getting a result, and that's what the optim function does. And here, see what happened. I told the optim function start with 50 and 0.1. I'm not quite sure how it made the other two triangle points. Probably it just added a little bit to these. And then it needed a total of 170 calls for the function. So I probably flipped the triangle 100 times, 115 times or so. And in the end, it found a point, namely this one here, and said the value is 40 at that point, and things have converged. This, I hope 0 means yes for the convergence. And what I can now do, I can ask me, is this what we want? Well, alpha should be 100, and we get 92. And kappa should be 0.035, and we got that in roughly. So this seems to have worked. Who of you had heard of maximum likelihood before or have ever used it? Okay, but for the others, that might be useful to quickly tell again the whole logic of doing well maximum likelihood. So this is how you do that in practice. And now that we've seen the general idea that we use maximum likelihood, one thing that's worth noticing at that point is what would happen if in my likelihood function I would have put the normal distribution at this place instead of a Poisson. What then would happen is that I take the logarithm of my normal distribution, and if it's only use the mean as the real parameter, then I have e to the minus x minus mu over sigma squared, and the logarithm brings this down from the exponent. So we have x minus mu squared. So we ask, what is the difference between x and the prospective middle mean value squared? So you see, this thing turns into the ordinary least square method if I replace the Poisson likelihood with a normal likelihood. This is why it's a true generalization, because if you put back the normal in, you get back to the ordinary least square. Simply because once you take the logarithm of a normal distribution's probability density function, you will see the least square criterion emerging. So, and now we can bring this into a more general form, which is this generalized linear model. Generalized linear models, they always were defined as having 3 parts. The first part is what we call the family. It tells us we have a response, so the values that we want, the y values of our regression, and we say this response follows, in our case, a Poisson distribution. And in general, you always specify a distribution with one parameter, and this parameter is, and you say my response follows this distribution around this mean parameter. Second, you say that the mean parameter depends on a linear predictor by a link function. In our case, we say the linear predictor is the log of the mean. That's why we call this a log link. And third, the linear predict with eta then is a linear combination of known predictors xij. So you see, you do your usual regression where you say you predict some value eta, which has an intercept, plus a linear combination of coefficients times some data points. And they together give you an eta, but we don't use this eta directly to compare it with our predictor as we would do in ordinary least square. Instead, we push this through the inverse link function to get a mu, put that thing into take the likelihood of that thing and then maximize the likelihood of this thing. Yeah.
I was wondering, you said a mean parameter and this not just for the plus one, or should we always use distributions which can be characterized by them?
Usually it's always a parameter, yes, you always put it in a way that it's a mean. You have also the binomial GLN, you always push it in a way that it's something which either is the mean or is proportional to the mean. You can also try to, there's some ways of getting around it, but in the classical formulation of a GLM, you reparameterize your distribution such that one of the parameters is the mean. The other parameter is usually you either set it constant or you try to, or it needs some special treatment. And we can now recover that our question here has exactly this shape. Because in our case, we say K is a Poisson, and the mean parameter lambda is alpha times e to the kappa tau. And if I push this through my link function, which is a logarithm, this of course turns into log alpha plus kappa tau. So log alpha is the intercept, and kappa tau is this, and kappa t is this thing, where t is the predictor x. So this here is the logarithm of that thing here. And it can be read as a linear predictor because it has an intercept and one thing which depends on our predictor, the pseudo time t, or sorry, the actual time t. And hence, the intercept is our initial activity, or actually the logarithm of the initial activity, and the slope is the decay constant. I added here a third parameter, OI, which is always added even if which is called the offset. And you see the difference from these ones here is you don't fit them. The betas are the functions which you fit. So the way how you fit with GLMs, you give it the case, you give it the X, and you give it the O, and you use maximum likelihood to find the maximum likelihood values for the beta. So I should probably have put this here, the case, the O's and the X are the input and the beta are the output. And the difference between the X and the O's is the X get multiplied with some beta which is supposed to be fitted, and the O's are used as they are. And they are called offsets. And the point of these offsets is, in our case, if you push the offsets O now through the log function, they become not an addition, but a multiplication here in front of this Poisson. And this would be, imagine we did our measurement here, and here I said in the beginning, we imagine that this here are hours, and every time we spend 1 minute sitting next to the Geiger counter. But now maybe we have the idea that we say, here at the end, after a minute, we haven't heard a single click. Maybe it makes sense to now wait 5 minutes. So we might have decided to wait a longer time here than here. And in order to account for this, we simply would put the logarithm of the time that we waited for a click as offset into our model. And then we get this out. And in R, we can do this. We have this GLM function, which we can now use instead of a general optim function. Whenever we can bring a maximum likelihood problem in this GLM form, we can use this GLM function where we say we want to regress K on T. So this formula is understood by R as meaning the response is K and the predictor is an intercept plus a coefficient to be multiplied with T. If you add T plus Q plus S, then it makes it better for each of them. And when we tell it the GLM family, which in our case is always a specification of the probability of a distribution, Poisson, and the link function, which is in our case the logarithm. And if I call it with this, you see here the coefficient is 4. It returns exactly the same values as before, 0.03427, 0.03427. only for the intercept, it has reproduced 4, and here it was something else, but this is simply because we have to, the kappa is, of course, in one case we have the kappa was the denominator here, and the other one was what was it? Yeah, we simply have to exponentiate it. That was the point. The alpha is fine because here the beta naught is the logarithm of what's called here the alpha. So I have to exponentiate what I get here. And if I exponent it, I get 92.388, which is exactly what gives us what the optim gave us. So we see both of these things have optimized the same function. The difference is that the GLM function doesn't use Nelder-Mead. It uses something called iterated reweighted least square, which works as follows. It takes the predictor, it takes the response variables, and then see if I get it correctly. In IRLS, you take the response variables, push it through your link function, so you take the logarithm. Now you make a linear model. You solve the linear model with ordinary least square to get a first guess. When you use this guess to get the predicted value, so the expected Poisson count for each data point, and that gives you not only the value which you have to put into the Poisson, but also the expected variance. And then you can go back and do a weighted maximum likelihood using these variances as weights that you calculated. So I was wondering when I wrote this up, I was wondering about, do I want to do this? And I thought, let's see how good ChatGPT is at making lecture notes. I can show you here what it did here. I simply tell it, explain ERLS fitting for it when it said what I've already told here, linear predictor and so on. And it said here what it does, each iteration, it makes some Taylor expansion, linearizes it, blah, blah. In the end, it makes a weighted least square. Then I complained to it that here it gave us the detailed algorithm. When I complained that it said here that we built the inverse, which in my memory from the textbook is wrong. And it said, yes, this is correct. We don't do this. Instead, we do this. So this is typical ChatGPT. I've noticed this a lot. Often it gives you this sort of simplified version with some mistakes when you say, no, this is not how I remember it from the last time I looked in the text. It says, yes, you're right. I've neglected to explain this detail. And then you get the right version. So it's useful to make a write-up if you already know whether, what it should write, because then you can check it. But I don't want to waste time now to go through this. If you are interested, you can have a look at it. So what we can now do with this, we can now use this GLM fitting for our local regression. And that's what I do here now. Let's go back to our data. This is still, again, the creation data, how I create my data again. Random X values. Some randomly chosen totals S and counts K, which follow with Q times S. And we plot this. This is what we had last time. And yet, instead of a kernel smoother, I do this local regression. So again, I write my function, which gets a point X naught and all the data and a smoothing bandwidth. And it calculates the kernel weights around our query X position. And now, as similar as we had before a linear model, we now call a generalized linear model, where we want an intercept, a beta 1 in front of X and a beta 2 in front of X squared, so that it fits us a parabola rather than simply a line. We want weights. We want offsets. This time we need offsets because the total number of reads we get from each cell is exactly the same thing as what I said before about the number of minutes we wait for the Geiger counter to click. The longer we wait or the deeper we sequence, the more values we get. And if you look at the math precisely, then you can see before I told you the exposure, so the length that we have to wait, goes here as a multiplicative factor in the Poisson expectation. And this time, the S is a multiplicative factor in the Poisson expression, so its logarithm goes here as offset. And I can do this, and the GLM gives me now the coefficients. I can use the coefficients to recalculate what's my value at x naught, and what I calculate here is the linear predictor. So I haven't exponentiated it yet, but that's fine because I want to make, here I have a logarithmic y-axis, so I stick to that and say I want to see this thing. And now, as before, I take a grid of x values, and for each of these grid of x values, I enter it in my function, and I get the red line, which now follows this thing quite nicely, only here it has a bit of problems. But interesting, what it now really nicely manages is to notice that up here, we have more non-zeros than zeros, so the curve goes up, and here we have more zeros than non-zeros, so the curve goes down. So it nicely manages to follow the curve. Only here the function has a bit of a problem that if it sees only zeros or nearly only zeros, of course it knows that the true rate is below the rate which would give one count, but it doesn't know how far below, so it might get a bit too low, and that's what's happening here. In that case, if you run that, you get a lot of warnings that the IRLS hasn't properly converged. But again, we can simply use the logfit package, which does all this automatically. We tell logfit that we want to regress k on x using a linear polynomial and Poisson thing with log link and so on. Log link isn't specified because that's the default, and then we get this thing here, which looks more or less the same. Yeah.
Did we regress using two predictors before, 2x and x squared? Like Wagner was now specified as a linear polynomial?
Two predictors?
Yeah.
Yes, exactly. While talking about this, I was also wondering. I used here the quadratic, and here I used the linear. I should run it again and see if it makes a difference. Yep, but well observed, exactly. Here we use the linear, so it's not surprising, but it's surprising similar. An annoying little thing which really drives me crazy every time I do this myself is you see here how we have to put the s as logarithms. And here in the logfit function, I don't have to put the logarithm because it does this internally. There's a whole book on this logfit. And nowhere in the 150 pages of this book does it spell out that it wants the unlogarithmized offsets. So this is a bit an annoying part whenever you work with numerical libraries. Often these things which are obvious to the author are not at all obvious. I mean, both would make sense that you have to specify the logs or not logs, and you can really curse the people who then forget to write this down. So, that was part one. And now, just because I like smoothing so much, I show you a second, completely different way how to do smoothing, which is called spline regression. And spline regression works as follows. To explain spline regression, I forget for the moment about Poisson. We will see that in the end, we can easily put the Poisson back in, because in the end, it will be a linear model, and we just have to replace the linear model by a GLM. But to see how it works, let's again imagine that we have normally distributed data. So you remember this was the original data which had normal noise. So the amount of noise up here and down here is the same. So, and what I now do is I make a spline basis. This here is the spline basis. My pseudo time runs, my x values run from 0 to 1. And now I have here a list of 1, 2, 3, 5, I think of 8. Now how many? 3, 4, 5, 6, 7, 8, of 9 functions. And these functions all have a couple of interesting properties. Namely, all these functions always add up to 1. No matter where I am on the x-axis, if I add up the value of all 9 functions, I get exactly 1. Second, all these functions a piecewise polynomial. So from one gray line to the next, they are a polynomial, and in that case specific a cubic polynomial. And third, each of them has a support over 4 of these segments that are bordered by the gray lines. And you always do. And what we now do is we can imagine that by making weighted linear combinations of these 9 functions, so we multiply each function with a weight, we can get rather diverse functions. If I put a lot of weights on the early function and little weight on the late functions, I get a function which is high first and then goes down. Or the other way around. You can also imagine if I just put weight 1 on all of them, then your result will be constant, because I've just said they are designed to always add up to 1. Yeah?
Did you say that the functions are only supported on all these square rectangles?
I hope so. Maybe it's 5. 1, 2, 3, 4. Except for the ones at the border, they are supported by less. Yeah.
Okay, because it looks to me like this light blue one has support early on, and then it's
1, 2, 3, 4.
But then at the very end, is that a separate function?
That's another one. Sorry. Okay. That's not the same, right? Okay. So here, these are the things that I've just told you. And because they're all piecewise polynomial, they are twice differentiable within the gray things, and they are chosen such that the first and second derivative at the gray lines, so of the left piece and the right piece, are the same, so that the derivative is smooth, and also the second derivative is continuous. And what I can now do is, I can now again do my data as I've done it before. I take my true function and add the noise, which is exactly what I've done before. And now I want to find a smoothing curve f of x, which minimizes the least square criterion. So the actual value yi times the value f at the position xi, so yi and xi are the data points. And you get here this least square criterion adding over all data points. And for f of xi, I put in here my basis function times a beta. And you will notice this is a least square problem. And this here, bs of x, even though it's written as a function, these are actually constants, because once I have a fixed list of xi values, that's what my data is, and for each of my xi values, I can calculate each of the 9 basis functions, and so I get a big matrix which gives me the value of each basis function at the position of each x value in my data, and that gives a big matrix. And that matrix is then precisely our usual square problem, where we say this matrix has to be multiplied by a coefficient vector and an intercept added, and that is my y. Which means I can use my standard linear model function, which takes here a matrix X and a vector Y, and then solves the problem Y is beta naught plus X beta plus some random noise. And we want that this random noise is minimized. And as you can see, the beta and this X is, as I said, the matrix of the 9 basis function evaluated at all the n data points. And if I put this in here in the lm_fit function, last time I used lm with the formula notation. lm_fit works the same, it just wants the x and the y, and then it gives you the coefficients, and this is the weight that we have to put on each of the 10 basis function. Okay, I miscounted. And if I then add up the 10 basis function, I get this red function, which, as you can see, looks actually nicely like, which actually nicely follows the blue line. So very different way, no kernel. Instead, we add it up by making a function space spanned by this 10 basis function and find within this function space the function which is closest to the data. So one problem is if you increase the number of nodes, like having more basis functions, then of course the function will get wiggly, like this here. And that's a bit an issue if you use only few basis functions, then you're quite restricted in what you can express. If you use too many basis functions, then your result will get a tendency to be wiggly. You could now try around until you find the optimal basis function, but there's two better ways. One is to use curvature penalization. As you can see here, wiggliness basically means that the second derivative has a rather large value at this point. So we might say we integrate up the second derivative here, squared, along the whole red line, and say this second derivative, this integrated second derivative shouldn't become too small, shouldn't become too large. So I change my objective function by saying I want to minimize this thing here, the least square criterion, plus the curvature penalty. And the lambda is a weighting factor which tells us how we weigh these two criteria against each other, because the more wiggly the curve is, the slower this thing will be, but the more stiff the curve is, the harder it can follow the data and the bigger this will. So there's a trade-off in either minimizing this or minimizing that, and the lambda directs the optimization, how important each of it is. Which means the bigger I make lambda, the stiffer the curve will be, and the smaller I make lambda, the more wiggly it will be. And here's the smooth spline function, which does exactly this. And then it looks like this, and you see now it's much less wiggly. Now, how does the smooth spline function optimize this thing? That is actually quite beautiful math, so I want to quickly show this. But before I want to, how much time do we have? Show you one other thing, which is quite neat, how this B-spline basis is actually constructed. You remember this basis function, I just put them here and said they have this property, but I didn't tell you the formula. So they are constructed with something called de Beer's construction. And de Beer has suggested the following. He said, let's start with a zeroth iteration where each basis function is simply a rectangle. It's one within its segment and it's zero outside its segment. And then let's make a second function where we always combine two neighboring zeroth basis function into a new basis function by interpolating between them. We move simultaneously from here to here, and while we move to the right, we always take the mean of this value and that value, this value and that value, and change the weight so that at the beginning we have all the weight on this side, and at the end we have all the weight on that side. So you can imagine here, we say we construct a first degree basis function, which is a linear interpolation between two neighboring ones before with a mixing ratio, which slowly goes up from 0 to 1. And as you can imagine, if you slowly go up, then of course you get triangles. Because if I interpolate between the red and the black here is 0 and the red is 1. So while I go up, I get this thing. This way I get these, and now I do it again. I interpolate between one triangle and its neighboring triangle by adding them up, and first using mostly the black, and in the end using mostly the red. You do that, you get this thing here. And you can imagine if you do this, we start with the triangles, which are piecewise linear functions, and the weight is also a linear function, which linearly increases from 0 to 1. If we multiply them, then we get a second degree polynomial. And if we do this procedure another time, then we get third degree polynomials. And each time the support increases gets one more segment. And this is how we get now this final third degree polynomials that we can now work with. Yeah.
The very borders.
Borders come in the next page. So here you see how this works. I can write this as a recursive function where I say my B-spline function at position, evaluated at position X, the basis function number S in the kth iteration of this procedure. So if I want, K is the degree that I want. And here this is the knots vector, so where these gray points are. And what I do, if K, the degree is 0, so constant, we just say, well, if you're between not S and not S plus 1, then give a 1, otherwise give a 0. If K is greater than 0, then we mix things of the previous ones. So we take the B-spline function at degree K minus 1 with the same knots, the 1 at position S and the basis function 1 to the right, evaluate it here, and now we weight them with this thing which smoothly goes up from 0 to 1. So to the left of this S, this here is to the left of the support, this here is 0, and this here is 1, and this here is 0, and at the right end of the support, it's the other way around. And you can see this is a recursive formula. So here in code, it calls itself, but you can also write it down, and we call this the Cox de Beer formula. And if we use this, then we get this plot here. And here I quickly have to mention who is Cox and de Beer, and this is quite interesting, my point. We call these splines. Why do we call them splines? Let's see, no. How is it? Yeah, this is a spline. Originally, if engineers or technical draftspeople wanted to draw a curved feature in some technical plan, they would use a bit of thin bendable wood, span it between two things and spline it, and this construction was called a spline. In the 40s, people tried to be more numerically, and the problem appeared especially in car manufacturing, because if you design a car and you want a nice, smoothed surface, like the bonnet should be nicely curved, think of an old style Volkswagen Beetle or whatever was modern in the 40s and 50s. You want something like this, but you also want to be able to scale this up from the plan to the full size of a car, and ideally you want to do this in a numerical way so that it's reproducible. So the car manufacturer, the car designer wonders, how can I create this with a mathematical construction? And there were three people involved who came up with ideas: Cox, de Beer, and Bézier. Bézier you might also know from the Bézier curve, which you always see in Illustrator. And actually the mathematics behind Bézier is pretty similar to what we've just done. It also has the idea of following two lines and interpolating it with linear weight. Yes, and I think Cox worked for General Motors, de Beer for Citroën, and Bézier for Renault. So all this math here is car manufacturers' math, which is interesting, where you can find where applied mathematics always gets its stuff. So last point, you just ask, how did it work to make the borders differently? Sometimes you have a fixed support from 0 to 1, and the idea that they had there is, let's just move the knots so that the first three knots sit more or less on top of each other. And you see here, I've done this. I now set the knot. I want to have 4 knots which all sit at 0, with maybe only 1,000 difference so that you can see it. And at the right, I want 4 knots which are all 1. And then I get exactly the thing that I've seen before. This is what the BS function of R gave me, and this is my own construction with my own function. You see, it looks the same. Only issue is here I've cheated slightly to make sure to put a little 1,000ths between the knots, because otherwise my formula has here at the bottom, all these denominators will become 0, which of course isn't a problem. I can form the limit, but there's a lot of paper and pencil work to calculate the limit correctly in all the special cases, so I couldn't be bothered. And now, once we have this, we might again want to do this curvature penalization that we used before already for the wiggliness. And what we do for this now is the following. If I have my degree 3 spline here, I can of course calculate the curvature because I have with the bare formula, I have a recursive formula for the function, and of course I can take its second derivative to get a recursive formula for the spline basis. As these are third degree polynomials, the second derivative should be a first degree polynomial, so it should be a line between each pair of basis points. And this is exactly the case. This is how it looks like, the second derivative. It's a line always piecewise from one knot to the next. I calculated it here with finite differences because, yeah, going through the whole data is too much work, especially once you pull in the knot points like before, because then it looks really weird. Now this means that if I now want to actually calculate here my penalty term that I need for the least square, I can do the following. This here is my spline squared, and if I now add this up, what's the nonsense here? I've written nonsense here. Imagine there would be 2 primes here. So the square of a second derivative of f. And what I have to do is I write this is f is now written as s times beta s, and this bs comma 3 should now not be the basis function, but its second derivative. So this line here. Imagine 2 primes here that are missing. And here it's the same. These are also 2 primes. And if I now, so this square I have expanded in this, I probably make this as a double sum with here my 2 coefficients. And this thing here that I'm now, I've pulled the coefficients out of the integral. And this thing here, this is now something which I can pre-calculate. I can pre-calculate the integral of the second derivatives of any mixture of 2 splines. So that I can write this whole thing here as a matrix vector times p times vector. And this is now, and this now means that my whole least square criterion can be written as follows. I have here my usual least square y minus fx, and here I have my integral over this thing. This thing I write out as y minus x beta times both times y minus x beta. And this thing we've just learned we can write as beta times some matrix p times beta, where p contains this pre-calculated values here. And if I now multiply this out, in the end, I get this thing. And this is what I want to minimize. And in order to minimize it, I take the gradient with respect to beta. And if you take the gradient that's constant, here the gradient vanishes and you stick with a 2xty. And here the gradient also vanishes. We have a square, so this side vanishes, this stays here. And then you get this thing here, and this thing should be 0 to find the minimum of the gradient, which means we pull this on the other side. And when we are left with this thing, and this is called the normal equation. It's a standard way how you solve for a linear, an ordinary least square problem. For a normal ordinary least square problem, of course, this term is missing, but you see there's no problem of adding it. And the nice thing about this normal equation is that it's actually very easily solved because y is a given vector. So this here is a vector, which you know. And this thing here is also a matrix which you can calculate. So you have here something like A times some matrix beta is some other matrix. And that's simply a linear equation system that you can solve with Gauss elimination. Or if you do Gauss elimination on a computer, you call it QR decomposition, but it's the same idea. And now you know how this smooth spline works that I've put up here, which, as you can see, finds a spline basis by simultaneously keeping the curvature limited. And the very last thing, I still have 5 minutes and it's very quickly said. There's an alternative to the curvature penalization, which is this one here, my new cost function. To the left, it's again what we had before, the least square criterion. Only this time I've written it not as a sum over the data points, but I just say this is a vector of y's and this is a matrix of x values, so I can write it as a Euclidean norm squared of the vector of responses and the matrix of predictors. And now I have a new idea, namely another way of removing the wiggliness is saying, if you look at this thing, wiggliness always happens if a coefficient of one value of one basis and the neighboring basis differ a lot by each other, because if they are the same, they add up to 1. Remember, we are constructed to add up to 1. So if you add up a couple of them, then in the middle we give 1. I think I even had a plot to show this. Here you can see this. Here the gray line is the sum of all of them, and you see in the inside they are all linear. So wiggliness happens by the fact that one goes down and the other goes up. Actually, this is, and if I want to, if I simply penalize this fact that neighboring splines have widely different coefficients, this also allows me to restrict the wiggliness a bit. And this is why we now have this penalty term, where instead of penalizing the curvature, we penalize the difference between neighboring coefficients. With a slightly different penalization. In one case, we don't want curvature, wiggliness. In that case, we don't want big jumps up and down. So that if the data is, if we don't have much data at some point, it should just keep everything on a constant value, which is, depending on your thing, it might be better to say, so for example, a line which straight goes down, linearly goes down, has no curvature, so it's not penalized by the first method, but is penalized by the other method. So this thing wants things to stay horizontal, the other thing wants stuff to stay straight, even if a straight line is not horizontal. And if you now compare this with the method which we had above here, we see that it again takes this shape here of x, y minus x beta, because this thing here can also be written as a matrix. We can bring it in this shape of, where did I just have it? Here, beta t p beta. This quadratic form, beta times p times beta, I can write this penalty in that form. And I do this by using this matrix here as p, because if you put a beta here and a beta vector here, you see that you always get something like beta 2 minus beta 1 minus beta 2, beta 1 minus